Okay, hi there, guys. We're about to do 2Q, and when we were talking about transformations last time round, I started waffling about transformations, translations, dilations, or stretches, and there's things that you should know about. And I said, well, that's just not turning up in that last exercise. Well, it's okay. That is turning up next, so that's fine. That's coming. Okay, and it's basically transformations here, which is taking us up to the end of this unit of work. Okay, and there's a lot of graph work to do, and we start off with 2Q with one idea, which is talking about how to create a function which is a reflection in the x-axis or the y-axis. So let's just look at this little box here. By the way, there's an investigation here. Have a look at that one as well. Now, the reflection in the y-axis is made by replacing all of your x's with minus x. Okay, so it's just switching your x-axis around. It's reflecting about the y-axis. That's this first little comment in the box. And the second one says y equals minus f of x is a reflection of y of equals f of x in the x-axis. So that one's relatively obvious, I think, that you're changing your positive heights to negative heights. F of x is a height, of course, and we're changing them from positive to negative or negative to positive. Okay, so that's pretty straightforward, to be honest. So we'll have a look at example 32, and then this one is going on to translations. And we'll just deal with translations here. It's not dealing with stretches as well, so it's going to get more complicated next. That should be pretty straightforward for most people. But there are a lot of examples here, so let's go through the examples. Okay, right. So example 32 says sketch the graph of f of x is equal to this function here. So let's just still on that. Do that. So we've got x is equal to minus 3, and we're going getting another root here. X is equal to 1, and then you can put in your graph. It's going to be a positive x squared, and we could now put on this axis here if we wanted to, so our y-axis. Okay, and the point in between those two is minus 1, so I know that this point here, just out of interest, if I put minus 1 into these functions, I'm getting my turning point out, which is 2 times minus 2, which is minus 4. My scale is quite different on the y-axis to my x-axis. Okay, it says clearly label any intercepts or extrema. I think I've done that, though I haven't actually put in minus 1, minus 4 as my extrema, as my minimum turning point there. I've got my little 0 there as well in the corner. Okay, so we've got the intercepts. That's all done. That's good. Now, on the same set of axes, reflect f in the y-axis and b in the x-axis. So let's do the first one then. So reflect in the y-axis, then we should be getting, instead, should be going still through, oh, we missed this out, still through this intercept here. Not very good. Okay, still going like this. So this version, let's put it on in here. By the way, I forgot this point here. Again, it's getting pretty messy, this one. So obviously, if I multiply out the, I put x is equal to 0 in there, I'll just get plus 3 times minus 1. So that's actually going through the y-axis intercept of minus 3 there. This is also going through the coordinate point 1, comma, minus 4, again, because we're getting a reflection in the y-axis from this graph. That's going to shift across to there. And again, although it's going to go through minus 1 there, it's also going to go through plus 3. So it's basically a reflection there and a reflection over there as well. So there's a 3. So there's that graph. And if we're going to do a reflection in the x-axis, the whole thing is going to get really messy. And hopefully you're not watching this on your phone where it's totally small. So x-axis, reflecting the x-axis is going to go like this. It's pretty easy though, right? So it's going to go like this. And I don't know where it's going to go down there. Okay, but it's going to go something like that. And then we can put on our turning point for this one as well. And we can say that this point up here color. So this point up here is going to be -1, 4, and this coordinate point here is going to now be 3. So we're shifting that upwards, and it's still going to go through the same two roots or zeros there. So I think that one is done. Okay, so I've just drawn out that graph again because it was a little bit messy. So for the first part, A here, when we've got this reflection in the y-axis, that's the reflection here, and we've now labeled everything that we need to. We've got where it's crossing the original axis for the original graph, and where it's crossing the x-axis again for the new graph, and the -3 where it's crossing the y-axis intercept. And our extremo, basically the turning point, although that's not a particularly well drawn or a particularly good a scale there, you can see, because actually that's not quite hitting my the bottom point of this graph. But okay, it's a little bit better than what we had before, and at least it's not the two graphs being confusing on there. Okay, so remember that this was the original function, and the reflection in the y-axis is f of -x. So it's saying, for example, if we put in, I don't know, x is equal to 3, then f of -x, we're actually plotting f of -3, which is over to this side, which is a 0. So f of -3 is equal to 0. So we're now plotting a 0 at 3. So everything on this side is now getting plotted on this side. And of course, the same happens with everything on this side gets plotted over to this side. Okay, so that's what we're looking to do. So this is kind of interesting algebraically, because we can now say we're looking for part A, f of -x, and that just requires us to replace all of our x's with -x in those functions. So we've got -x minus 1. And we probably want to tidy that up a bit. I could take a factor of -1 out of this bracket and bring it to the front. So now I've got x plus 1 there. And then the other bracket I could write the other way around. I could write that as 3 minus x. That's a little bit neater. But then actually we could absorb, let's just keep that there, we could absorb the minus into this one. So let's absorb the minus into there, and it just switches it around. Okay, and that's actually exactly what we expect, isn't it? Because we're expecting a root at -1 and a root at 3, root at -1 and a root at 3. Okay, so just a little playing around gets us out the function which we're expecting in the first place. Okay, now let's see how much I can get back. Doesn't allow us to pick back everything. So here we go. For B, now different graph for B. I'm not going to do the whole thing again. So for B, though, roughly speaking, we had this graph is now reflected in the x-axis, needs to become this graph here. So where previously we had roots of -3 and 1, we still have those roots. We just have the reflected extrema, our minimum turning point now becomes a maximum turning point. Now, that's just minus fx, so we can do minus x 3, and then x minus 1. And again, we can absorb the minus into one of the brackets here, so we could say, actually, that's x plus 3 and 1 minus x. We could do that if we wanted to. There you go, that's done. Both of those are valid answers, by the way. Okay, so let's have a look at the answers they come up in the book there. They've actually multiplied out the brackets in that case for f of -x. And yeah, they've basically come up with exactly the same as I've come up with a minus. We've actually multiplying out the bracket for part B as well. Okay, well, let's shift on from there. We're talking about translations next. Yeah, okay, well, these have turned up before, basically, that's what it's saying there. And there's a whole lot of different translations here, just describing translations, but I mean, there's a lot of words for basically saying that, let me check it out. We go to Desmos, it's say, let's put in a function for this one. Let's say f of x equals to, let's come up with x squared, keeps it nice and simple. And then if we want to do a translation by a vector, well, if we want to move it forwards, we could put in, let's say, let's move it forwards 2. Okay, so remember I said this before, that's essentially taking all of the answers from 2 before and putting them where we are now. So for example, at 2, we take the answer from the original function at 0. That's the effect of doing this take away 2. That's why we're putting it forwards by 2. We're taking the values from before and plotting them where we are now. So that's f of x minus 2, but remember anything that happens outside of the brackets happens in the direction which we expect. So whatever our height is there for these, if we want to shift it up by, let's say, 1, then we just need to put a plus 1 in the end. All of those heights which we have, we can just go forwards by adding on 1 to make those heights 1 higher. Okay, now that's the transformation of the vector by the vector a, b. So a on the top, b on the bottom. Now, of course, we can make that a and b there if we want to, and we can add sliders for those things. And we can just change the a, moving it further forwards if we're making it bigger, and backwards if we're making it negative, in fact. Okay, so that's going to give us the vector transformations. Let's get rid of this just for a second. So if we say f of x minus a and plus b, now that's going to give us the translation of a and b. Now I've kept a and b being positive as I was talking there, but of course if a is negative, that actually takes us backwards. So it's going to look like a plus b there. Okay, this is fine. Okay, we're talking about translations. If we go from f of x to this function here, then that gives us a translation of a, b for our original function. Remember, with vectors, the a represents the horizontal shift and the b represents the vertical shift or translation there. Okay, we should say translation, not shift. If you say shift, you're going to lose marks in an exam. Okay, so let's look at example 33, and there's plenty of examples here. So example 33 says, describe the transformations necessary to obtain the graph y equals x plus 3 all squared plus 1 from the original graph of f of x or y equals x squared. So what's happening here? Well, there's two transformations. There's two translations, in fact. We've got the translation of 3 backwards, because remember, we had it in the form of a minus b there. So sorry, x minus a there. So it's going to be 3 backwards and it's going to be 1 up. So this is the translation. We can simply say this is the translation by the vector. And there we go. Or we could say this is backwards 3 units in the x direction and forwards 1 unit in the y direction, or up 1 unit in the y direction. Okay. So there we go. That one's done. It's easier to talk about things in terms of vectors. So we've done that, and it says state the coordinates of the image of the vertex under this translation. So the vertex of this graph is at 0, 0. So the new vertex is going to shift forwards, or translate forwards, backwards rather, by 3, and it's going to go up 1. So we just need to take 3 off this and add 1 onto this. So it happens to be the same as this, but only that's a coincidence because we started with 0, 0. So basically, on all of our points, we'll have to take off 3 here and add 1 here. Okay, so that's the image of the vertex. That's done. That's this point here. And it says sketch both graphs on the same set of axes. Well, you can do that. It's pretty straightforward. I mean, a little hint, of course. Remember what I said before. If we've got the original graph, Going across one and up one to take you to this point here is always going to be that sort of second point after we've got our vertex. So when we use the vertex -3, comma, somewhere over here, comma 1, so that's going to be the vertex of the new one, then the graph is going to look something like this. We should probably say where it crosses the axis as well. So try and fit that on too. But yeah, the next point across is going to be 1 across and 1 up, and I've talked about that previously. Okay, that's done. So look, sketches of those graphs, fine, done. They actually haven't shown where this crosses the y-axis, so fine. Don't worry about that. I would always try and come up with the points where we're crossing the axes. In other words, the y-axis intercepts and the x-axis intercepts, if I can possibly fit them onto a sketch. And of course, if you've done the sketch badly the first time, then just redo it. You put a line through it and redo it. Okay, vertical dilations and horizontal dilations. Oh, okay. Sorry, I thought this was turning up in the next bit. Okay, well, this is relatively straightforward. So let's have a little look at these ones. So essentially, they're talking about stretches here. So vertical stretches and horizontal stretches. Let's look at this through Desmos. Okay, and this is not a good one to use here. So let's use sine of x, brackets there. So if we said now we want to do 2 lots of f of x, so 2 lots of f of x there. Okay, 2 lots of f of x is essentially stretching everything in the y direction by a factor of 2. Now that's also called a dilation. So when they're talking about dilations, they're just saying what's the stretch. But we can always talk about things in terms of stretches in the y direction or stretches in the x direction. Now notice that everything which is on a 0 stays on a 0, and everything, any height now becomes twice as far away from the x-axis. Okay, right, so that is that. We could also call that one, for example, g of x is equal to 2 sine x. That's exactly the same thing, of course. Okay, now if we took that 2 and put it on the inside, and I mentioned this before, that's now giving us a stretch by a factor of 1/2 in the x direction, or a squash by a factor of 2, but we don't say that. So a stretch of a factor of 1/2, it's bringing everything twice as close in. So for example, I wonder if we can just change the axes here. So I know that you haven't necessarily done radians just yet. So let's put it in degrees, and it's going to look totally different. Then let's change this so that let's grid up to 400 degrees, say. Okay, let's go a bit further. Up to 600 degrees. Okay, and then let's take this down to 1 minus 100. Okay, so let's fit that in. Okay, so there's our graph again, and then you're kind of used to this. Oh, let's play around with this a bit more. Let's go up in steps of 30. There we go. So we've got steps of 30 there. Okay, so there's our 360. That's for the original graph. There's the original sine graph. I'm going to play around with this a bit more. Sorry about this, being quite annoying. Let's go down to -2 and 2. Okay, so there we go. That's a nicer graph. So our original function, that's this one here. There's the original sine function. It's ending at 360. Now you can see that we're actually fitting 2 of those sine functions in now in that same period. So we're doubling the frequency of this sine graph, and we are essentially bringing this point into here to make that the period half of the original period. I think you can see that, right? So essentially this is stretching by a factor of 1/2 in the x direction. Okay, now the reason why I didn't use x squared there is because if I said x squared was my original function, there we go. Oh, I need to go back to my original axes now. Tell you what, let's just add a new one. It's just much easier. Okay, And so if I say y equals x squared, this is my original function. Now, if I say, call that f of x there. Now, if I say f of 2x here, that just looks like a vertical stretch. It doesn't look like a horizontal stretch, but it is a horizontal stretch. It's just that it's also a vertical stretch. Because, of course, if we put in 2x into that function, we're going to get out 2x all squared, which gives us 4x squared, which is the same thing. So, in fact, with x squared, a vertical stretch of a factor of 4 is the same as 2x all squared. It's the same thing. It's the same as this function here. It doesn't like me doing two functions, but it's the same thing. Now, this happens to be, get rid of that. The f of 2x there is still true, because if you take, for example, the point 2, 4, that's becoming the new point 1, 4. Now, for stretches, you can see that on the original graph, all you need to do if it's a stretch in the x direction is change the x number by dividing it by 2, and then you'll get your new point. So all your points are coming twice as close in. If it's a vertical stretch, let's take, for example, the point 1, 1. So if you see it as a vertical stretch instead, by doing f of x is equal to 4x squared, then the 1 stays the same, but then the y value gets times by 4. So it depends on how you look at it. So that's why I didn't take f of x is equal to x squared. Okay, I'm going on a bit, but hopefully there's a sort of useful point. And you can obviously read all this one through as well, but I think we've gone through enough there. Okay, and now, whoa, okay, so then they just chuck in this thing here, and really this needs some unpacking. Okay, when we talk about the general transformation, in particular, this bit in the middle is difficult. So the order of the thing in the middle is difficult. Now, do I want to unpack that now? Because I know that that's turning up later. Remember that the thing on the inside, say for example, we went from f of x to f of 2x plus 1. Remember the thing on the inside is always the opposite way round to what you expect. Let's just take a minus 1 there instead. So this is kind of saying, well, this one, I'll unpack it a bit when we see it later. But this is saying, actually, instead of doing the stretch first by a factor of a half and then the translation by 1, this is really saying this is a translation forwards by 1 and then a stretch of a half. It's always in the opposite way round to what you expect. That's essentially because we're saying, let's take values which are twice as far ahead and then 1 backwards. So to undo that, we'll need to say, well, let's add 1 and then let's bring it twice as close in from the original function. And so wherever we get the answer from the original function, we'll need to take that 1 forward and then take it twice as close in. Now, you'll often see things written like this instead on the inside. So instead of that, if you had, for example, f of, let's say 2x minus 1, well, you need to take that the opposite way around to what you would expect as well. So normally you're thinking, well, I'm going to do this by doing the translation by plus 1 first because it's inside the brackets. But no, the thing here on the inside works the wrong way round. So this is actually a stretch by a factor of a half, and then it's a movement forwards by 1. I think we need to see a question on that one later on, but that's really where a lot of these questions catch you out. Anyway, these ones here don't have these double transformations on the inside. So example 34. Example 34. Now I'm going to actually copy this whole section because I'm not going to draw this. It's going to take me forever to do this. It says graph this piecewise function. And you'll notice that at minus 3, it's giving you the same answer for this as it's giving for this thing here, which happens to be minus 2, which is the end of the red function here. Okay, so the red function is the original function f of x. So we've got this minus 2x plus 8, in other words, minus -8. Should go through -8 somewhere down here. We carry on, and okay, so you can do that. You can plot some values there. It's not going to take you too long to come up with that, but you really need to space this out well and use lots of space. You can see I don't have a lot of space here. So that's between -4 and -3. And then it's saying 2x plus 4, so then we have a positive gradient. Should be going through +4 if we continued upwards there. Okay, so you can see it's actually crossing through 2, -2, 0 rather. Okay, for the next one we have -2x, and again, you're getting the same answer whether you put -1 into the second function there or the third one. You're getting out the height of 2 there when you put in -1. You can do this or this. Okay, and then you're getting this negative function, so -2. It's leading us back to 0 if we put in 0 in, and you're getting out 0 when you put that into this one as well. And then we're getting a shallower gradient of just x, a gradient of 1 rather, when we have y equals x at the end. Phew. Okay, so it tells us to label zeros and intercepts. It doesn't tell us to label the extrema, but they've labeled that turning point as well. Yes, it does. Sorry, it does, because it's following on the sentence here and the maximum and minimum points. Okay, so you really need a lot of space to draw this one, and the red graph is the original graph. Okay, so for part A, it's saying graph the transformations, and again indicate the coordinates of all the labeled points of the original graph. So graph 2f of x, well, all that's going to happen there is we're going to double all of our original heights. So you can see that any 0 stays at 0, any -2 is going to become a -4, and you can just go from those original green points and then just double all of those and then just join it up with a zigzag line. Remember that this definitely stops at 4,8 here, which is doubling the y value of 4,4. It definitely stops at 4,8. You cannot just keep drawing this one upwards. There is a restricted domain and a restricted range in both of these cases. You need to be clear where you're finishing for these graphs. Okay, now you might want to actually put that dot on the end there and put that dot on the end there, as well as putting that dot on the end there as well, just to say this closed circle is defining that there is an answer when we're coming up with that final point. But of course, the coordinate point tells us that as well. Okay, now f of 2x is going to take all of these all of the points on that red line and bring them twice as close in. So 4, 4 is going to become the point 2, 4. 0, 0 is going to stay the same. Okay, stay on the y-axis. The point 1, -1, 2 is going to be -0.5, 2, and this point here, -3, -2 is going to become the point -1.5, -2, and this point is going to go twice as close in as well, so that's going to become the point -2, 0 for this one. Okay, now so everything's going to be squashed in. Now let's have a look at how they do that. I'm sorry, I'm not going to do it myself because it's just going to take forever. And you can see that kind of by drawing the f of x graph more stretched out compared to the original one. I think it's more stretched out. Yes, it is. And then it gives you a bit more space to draw the blue graph, which they've come up with. Okay, example 35, then example 36, and then we're done with this. Lots of examples here. Example 35. Okay, so they're saying consider this function, and we're not even being given the piecewise function in this case. They're not asking for the piecewise function. They're just saying come up with these new sketches. I just discussed this really briefly. I'm not going to do them all myself, but 2 lots of f of x is going to double all of the heights. So I don't know, I can't resist. Okay, so there we go. It's doubling all of the heights. It's going to take us something like this, and it's going to take us up to 6 there. It's going to double all of the steepness. Okay, so again, we can double the height here, double the height here, double the height here, double the height here. Take your key vertices and do what you need to do with them. F of minus x, remember, is going to have the effect of flipping it over to the other side. So this one is going to be 4 down to 6 and then up like this. Okay, so that's the part B there. And then f of 2 of x, remember, is going to bring all of your coordinate points twice as close in. So it's going to bring it in like that. So the 6 is going into a 3, the 4 is going into a 2, and the minus 2 comes into a minus 1. Okay, so graph is going to be this, this, and this. So a bit messy. We can see the book version in a second. And for this one, it's talking about 2 transformations, or translations rather, or simply one vector translation of 1 across and minus 3 down. So that's 1 across for each of the coordinate points and 3 down. So that point, for example, is going to go there. So you do that for each of these ones, and you're going to get exactly the same shape. Pens out enough? Probably about you. Okay, and so it's going to follow that translation. Okay, so let's look at those. There's A, there's B, there's C, and there's D. Right, fantastic. Okay, well, we're actually going pretty quickly through these ones now. So last one here is saying for 36, okay, saying, pen is playing up, switch pens. It says functions G, R, and S are transformations of the function f. So this function in the center transforms to G, green one, R, blue one, and S, red one. Write down the functions G, R, and S in terms of f. So f of x is just your normal f of x. We don't actually know what that function is. We'll say what transformations are. So we can see that G is just a stretch in the x direction. And so take your point here, for example, it's going to stretch by a factor of 4 in the x direction. Now, that's going to take f of x is going to become f of a quarter x here. Okay, so in order to stretch by a factor of 4, we're going to need to take 1 divided by that stretch factor, give us the number in front of x. Remember, if we had 4x there as the coefficient, that would bring us in by a factor of 4. So the stretch, we've got a of x there, then the stretch is a factor of 1 over a. And so likewise, by taking the reciprocal of the stretch, we'll get the number in front here. Okay, so that's the first one. So to say g of x is equal to this thing here, f of quarter x. So that's done. So for r, what's r? We're saying r is, okay, so there's a couple of things which are going on for r. Let's clear everything out. So for r, we need perhaps a reflection in the x-axis will kick things off. That will get it the right way round. Perhaps there's more than one way of doing this. So a reflection in the x-axis and then a translation. So 2 translations, in fact, but 1 vector translation. So r x is going to be that f of x. Let's just take it through our steps, actually. So let's do f of x is going to become f minus fx. So that's the first step. And then the next step is we want to take that and then increase. So take the x value backwards by 4 units. So we're going to replace x by x minus 4, no, x plus 4, so it's the opposite of what you expect. So that takes us upwards by 4. No, it doesn't. It takes us backwards by 4, so I'm getting a little tired here. So it takes us backwards by 4. And then the final step will be to then go up, and we'll need to go up by 5 units. So plus 5 units there as well. So this is your final function. Okay, so we're getting r of x is equal to this thing here, minus f of x plus 4 in brackets and then plus 5 on the end. Just going to check that one to see that they've done it the same way. Yeah, okay, and they've made less of a meal of it there. You can see what they've said for r of x. Okay, so for the last one, okay, and so s in terms of f, well, s looks like a stretch in the y direction. Okay, so stretch in the y direction in this case, and then we can move the thing as well. So the x values between 3 and 7, it's a sort of distance of 5, and you can see there's a distance of, oh, no, it's distance of 4, sorry, and distance of 4 there, so no, that's fine. Okay, so there's no x stretch, but there is a y stretch. So f of x is going to need to become 2 lots of f of x, I think. Okay, because it's got a height of 4 is now becoming a height of 8. Right, so new height of 8. So let's stretch it to start off with. Now that's going to take this point here to 4, this point here down to minus 4. Okay, so 0, 2 becomes 0, 4. And after we've done the correct stretch, so this point is going to go to here as well. And, you know, it's going to go through there. It's going to go further down. Okay, and, you know, so it's going to be the right shape. Same for the other side as well. So it's still going to be the same W shape, but now we need to move the thing as well. So to move the thing, we'll need to say f of, let's take this central point here. It's going to need to go 5 forwards. So that's going to be x minus 5 in there. And it's going to need to go up by 4. So up by 4 there as well. We'll still have that 2 there. So this is our final function, and that's going to be what s of x is equal to. So that's equal to this thing here. Just check that one again. Yeah, okay, so there we go. So I've dealt with the stretch first, and then I've dealt with the translations. Okay, well, struggling a bit on that. That's exercise 2Q. You can have a go at the questions there. And there's 4 questions, lots of parts there as well. Oh no, going up to 4F. And next time around, we're dealing with rational functions and talking about rational functions being written as reciprocal functions if we play around with them a little bit. So some nice work coming up, 2 more exercises left in this unit. Keep putting in the good work, and I'll see you for the next one.